Okay. Just it didn't want to open. Yeah, I have the book open. So problem 2. Oh, it was problem 4 in your book, but it's the second one we're looking at. The other ones I didn't really type out. We talked about them though. But it says, explain how the time to peak rule confirms that peak production occurs when half of the resources are extracted. No. Remember in our model, C is the total extractable resources, so the total amount there. And M is the total amount that's been extracted. So if we're finding our peak time, and they said it was when we have half of it. So it's saying when we mine half of it, then we're at our peak. Well, the formula for the peak is the log, this one here, C over M minus 1 divided by the log R 1 plus R. R plus 1 would be the same thing. Now if M equals 1/2 C, we need C over M to plug it in. So we could solve this. We could multiply both sides by 2 to get C by itself. And then divide by M. That way we can plug in here. Now the rate's not going to matter what the rate is. When we plug in 2 on top, if you take the log of 2 minus 1, well, 2 minus 1 is 1. The log of 1 is 0. Now, by getting that 0, when we use half of it being gone, if you're getting 0, then that means you're already at the peak. The time to peak is now. So when half of, so if there was 500,000, then half of that, 250,000. When we've mined that much of it, we're at our peak. So that 0 doesn't mean you're done. It means that you reach the peak. You're already at the peak. This one was telling you when you would get there, it was 150 years before we'd hit our peak production. And peak production is when half of the resources or whatever you're mining is gone. Any questions on that? So when you plug into this formula, it tells you how long till you'll reach the peak. Not when it's all gone, it's just when you've mined the most at a time that you're going to mine. One of the most important applications of these ideas has been to study the likely courses of fossil fuels, oil, things like that. Figure 218 on page 218. When it does that. So on 218, figure 19, that's this one here. It's total production in billions and annual growth rate. And this is for oil. Notice that the more we mine the oil, the amount that we're gathering, or the growth rate is how much you're taking out. Those are decreasing. And it's pretty close to a linear model. It drops down a little more here, which maybe they need to do fracking or something to get more of it. And then they hit a spot that comes out really easily. So it goes up and down a little, but it's still staying on that linear trend. Any questions on reading the graph? The ultimate limit to U.S. oil resources, the carrying capacity, is where the line hits the x-axis because you've run out. And so this one, let's see, 200, it's around 210. Maybe a little less, but it's around 1, 2, 3. Yeah, about 210. And it's in billions. So we have approximately 210 billion barrels of oil, and then we will run out. The last plotted was in 1999 before fracking, a new technology that has been dramatically increased production of U.S. oil. Because of fracking, most of the recent few points, if we plotted them in figure 19, would be far above the trend line. I'm trying to move that. There we go. So in 1999, now because of fracking, then there'd probably be some up here, which then would change our line. Worldwide, there are many different oil producing areas in the world, all with their own production and depletion rates. Because all these variables, it's hard to give an accurate estimate of when global peak oil, the maximum rate of global production, is likely to happen. And so we can find our values and when our peak will be, but other countries have different types of mining. Some of them don't have oil, but those that do have different types of production. And so to try and say one globally, it's hard to say. But global peak oil is the year in which the world's production of oil is greater than that of any year before or after it. So it's when it hits its highest amount of producing or gathering oil, and then everything else is below it. And I believe 219 figure 20. So each of these peaks are different areas where it has a global peak because it went up and down. Figure 20, one example of a peak oil production forecast. And this is forecasted till 2050. Notice that US is this purple colored one. And we stay pretty uniform. We do hit a peak right here, but then it goes down. And we don't have anything. What's the dark blue? Deep water. So that looks like that's where the most is. And we hit our peak in 2010. So now we're mining less. Then this is where we hit our highest amount of mining. So the global peak oil, or even the peak oil for the US, is not when we ran out. The peak is when you gathered the most for that session, or in this case, year. Any questions on that? So when you're finding your peak, or when it will reach the peak, it's not when you're running out, it's when you're at half for the most part. Any questions on that? So it says, notice that peak oil does not mean when the oil runs out. In fact, its name suggests it's the moment when the oil extraction and the industry that it supports are at their greatest level. It's when they've produced the most. So if we look at how much they produce, in this case, each year, when they produce the most, that's your peak level. Any questions on that? Positive. I think that was everything in this section. Yeah. At the end of each section, they have the definitions. So you could always have them all together for each section. They have the main parts. This section, you know how we had the charts, the flow charts, and we put the plus and minuses. This next section, 4.3, is going to add values to those. Let me bring up the paper. Oh, I could have just went in my. I haven't finished 4.3, but I did put the link up there, and then as I finish it, I'll add to it. So what this section did was it took a lot of our problems from previous sections that we had through charts with, and it added values or percents or a rate. If you remember, I think it was 46% was the bathtub. And here's the bathtub one. Remember the faucet, put the water in, and then the water, this is our stock, and then it went down the drain. And the more water or the higher the tub, the faster it went down the drain. So more water in the tub increased the flow into the drain. Now we're giving it a value, and they're saying it's going by 0.46. Now this is gallons per minute per inch, and that's what they're showing you here. And then remember, our rate was times the height. But that's also your strength. If you look at example 1, well, it says, oops. In the bathtub model, the outflow rate is proportional to the depth of the height. Remember, we used R equals how much was in there times the height. And the constant 0.46 gallons per minute per inch. And that's what they're doing here. And then you multiply by your height. And this is figure, oops, that's for the next part. No, it's page 22. Oh, that's right page. The strength of the control in the bathtub example is 0.46 gallons per minute per inch. Notice carefully the units of the control strength, flow units, right here is 0.46. In another problem, we'll show how you find the total strength. I think they didn't do it here because there was no flow here. It was only here. In a proportional relationship, a change in the stock level affects the flow rate. Both the strength of the control itself does not depend on the stock level. We call this a linear control. So it's not just on this, because you also have some coming out here. And depends on how much is going in. In this case, they didn't tell us. A control arrow in a stock flow diagram is linear if the flow rate at its head is equal to C times S plus K, where S is the stock or parameter level, C and K are constants. The strength of the control is the constant of proportionality. And we get to that later in this section. At the beginning, they're just talking about it. So first they'll explain some other parts using previous examples. But this one, it was saying 0.46 here. Example 2 shows a little bit more. The caffeine problem, if you remember when we did that. If you wanted to go back and look at the caffeine problem, it's on 156. But they'll show you in figure 22 on the next page. Right here. It says, in the caffeine problem, we noted that the body metabolism's caffeine was at a rate proportional to the stock of caffeine in the bloodstream. This rate depends on a variety of factors, but the average rate is 15% per hour among healthy adults. Since the rate is proportional to the stock level, the control level strength is 15%. Now, the reason they have this h to the -1, it's just per hour. But when you have something in your denominator, Remember, if we have 1 over x, we can write it x to the -1. So it was 0.15 per hour, but instead of having it in the bottom, they can move it up. That's all they're doing. That's why it's to the -1. But that's where this -1 came. And then 15% divided by 100 to make it a decimal. So we said there's 15% per hour of caffeine, and that's why then this is 0.15. Any questions on that? So now we're going to put weights into it, and we'll be able to find out a little bit more. If you're looking ahead, this one has 2 different weights because population increases births and it increases deaths. Any questions on the caffeine one? It's just showing you how to put values in first. The next example is the population right here. Oh, too much. There we go. Remember, births are increasing and then leaving the stock is a negative. So this is the positive of the blue, and then this is a negative. These two, when we did them, were both positive because as the population grows, it increases the number of births. As the population grows, it also increases the number of deaths. So we have 2 stock flow models. This one is amplifying. This one is stabilizing. Any questions on that part? We can calculate the strength of the birth feedback loop. I think what they did was they found out the percentage of increase each year. They found an average, and it was 1.22%. And then deaths were approximately 0.75. Now, this negative, ignore it for a second. The 0.75 was this. That is on average approximately how many deaths we get each year. Any questions on the values? So what they did was they just did research and found out on average each year what percentage does the births increase by, and what percentage do deaths increase by. The reason they're making the strength negative, if we look at this feedback loop, a positive times a positive is a positive. That means it's amplifying. A negative times a positive is a negative. This is a stabilizing because it's a negative. So this negative is the feedback loop, the whole loop, not just this here. So be careful of that. You're multiplying the 2 values in your loop together. So if we find the overall strength, we combine these. This was a positive because a positive times a positive is a positive. This one's a negative times a positive, and that's why we're subtracting. So since your answer is positive, it's telling you the combined amount is amplifying. The fact that this sign is positive tells us that the overall feedback is positive, which means it's an amplifying cycle. If this would have been a negative value, then it would have been stabilizing. But amplifying means we're growing too much, which I guess is a good thing. Now it's saying this is exactly how we predicted the US population, neglecting the important factor of migration. People. So this is just the people who are here. If nobody leaves, nobody else comes in, then this is the proportions they were getting. They weren't including people who would move here and live, or if people here would move out. Oh. Any questions on that? Any questions on the level overall strength? As I said right here, this remark, you need to be careful to distinguish between the sign of a control and the sign of a feedback loop. This blue line is a positive and a negative. Now the control loops are the red ones. This one's positive and this one's positive. The loop, you multiply these together. So the feedback loop, you multiply them together, and then overall strength, you add them using the sign. So be careful of that. Any questions on that? Rules for measuring, I put them here. A feedback loop in a single stock system consists of a control arrow and a flow arrow. So a feedback loop has to have both the control arrow, which is the blue, and the flow arrow. Whoops, wait, control arrow and flow arrow. Yeah, there has to be both. The control arrow has a strength. So this red is the control, blue is the flow. The control arrow will have a strength, which is measured in flow units divided by stock units. Use the feedback rule of signs to determine the sign of the strength of the feedback loop. Multiply them together. To find the overall feedback in the system, add the strengths of each loop together. As in the feedback rule of signs, a negative overall feedback is stabilizing, a positive is amplifying. Any questions on that? Okay. In a hypothetical fish farm, there is stock S, adult tilapia. Every month, 1,000 young tilapia are added to the stock. 3% of the stock die from natural causes and 25% of the stock are harvested. Make a stock flow diagram and compute the strengths of the feedback loop. What is the overall feedback loop? Positive, negative. What is the equilibrium level? So first of all, we have fish coming in. There's a stock. So our stock is the tilapia. Oh, I guess they have it on here. I don't have to draw it. So we have the inflow of the babies. But then we have natural death and harvesting. There's two different ways that they leave. So this is an inflow, and then this is out. Put the weights on. I mean, so these are both going out. If this gets larger, then there's more deaths. If this gets larger, then they harvest more. Any questions on the arrows? So that would be your stock flow diagram. Make a stock loop. Compute the strengths of all feedback loops. What is the overall feedback loop? Well, the 3% of the stock die. 3% as a decimal 0.03. And 25% are harvested. The reason they're getting the negatives here is because negative times positive is a negative. So 3% die per month and 25% are harvested per month. And it's negative because they're coming from our stock. You just multiply these together. So they take out 28% every month. Any questions on that? So this is the strength, the overall strength. This would be a good problem for like the take-home portion of the exam. That way then you can try it and we can talk about it, but not have the whole thing. Although it's not too hard, but if I gave one on the exam, I would already have it drawn with the numbers. So then I know you know how to find it, but on the in-person, I'd have it already set up. The take-home, I'd want more of like a thought process like this problem. What is the overall feedback? That's the overall feedback or strength. Is it positive or negative? It's negative. And what is the equilibrium? Well, the equilibrium each month they're putting 1,000 fish into the stock. Remember, equilibrium, you want the amount going in and the amount going out to be equal. And that's why they're taking 28% or 0.28 of the stock because we said this amount of the stock is taken out each time. 3% to death and 25% to harvest. So that's 28% of your stock. That's taken out, and they said they replenish it with 1,000 fish. So those need to be equal to be in an equilibrium. This is the amount coming out. This is the amount they said they put in each month. So then you just solve for stock. This is being multiplied, so I divide. What did they round to? 3,600. Now, of course, you're not going to have part of a fish, so you have to round it to a whole number. 3,571 would not be wrong. They probably just rounded because you don't need all, you could just say round here, 3,600. This is almost another 100. We wouldn't want to go 4,000. That's a little too large, but 3,600, you really don't need that 71. And that's why they rounded to that. It's tilapia, right? So 3,600 would be fine. 3,571 would be fine. Whatever I asked to round to, they went 2 significant digits. They do that a lot. But any questions on it? Positive. We'll stop there. An equilibrium of a stock flow system is stable if after any small disturbance of the equilibrium, the system tends to return to its equal state. If you think about the train derailment and all the fish that died in East Palestine, that would be a case of a disturbance. But then hopefully, if they didn't completely wipe all of them out, they will return to an equilibrium point again. An equilibrium of a stock flow system that's unstable, if after any small disturbance of equilibrium, the system tends to move further away from it. So hopefully, I think it was a stable area to begin with. If it didn't completely wipe everything out, it should return to an equilibrium. But there are cases where if it's not stable to begin with, any little disturbance could just wipe everything out. So that's what they're talking about, whether it's stable or unstable. And we'll talk about the examples. I guess it will. Saw the water depth. Yeah, we'll stop there. Any questions?
Wait, so whenever it asks us to find the equilibrium, it's just like it's not like it doesn't have to be at an equilibrium. Like, what are we finding exactly? I'm a little confused.
Okay, so they were saying that when the fish were harvested and natural death, they're putting in so that to keep this is 1,000 fish going in. To be in an equilibrium, then you need 1,000 fish going out. So we wanted to find out how many were in here So that if we 3% died and 25% were harvested, it came to 1,000. Because to be in an equilibrium, the amount going in has to match the amount going out. And so we knew it was, because we combined these two, 28% of the stock was taken out every month. 3% per death, 25% per harvest. So we knew this. Oops, without the division. We also knew that they keep putting 1,000 fish in. So to be in an equilibrium, then these two need to be the same. Whatever the stock is, 28% of that needs to be 1,000. Does that help? That's why you're setting them equal. If we knew the stock was 3,600, say instead of 1,000, we knew the stock was 3,600. And we knew 3% died and 25% are harvested, then we could find of the 3,600 fish, find 28% of it, because that's how much is coming out. Written as a decimal times the 3,600 should get us approximately 1,000. Now, since we rounded, it'll be a little different. So what we were finding was the stock. And that's why we set it equal to 1,000, because this was the amount going in. This would be the amount going out. To be in an equilibrium, they have to be the same.
Right. So like we're saying like whenever we did the division, we were doing the division to find out if it were to be at an equilibrium,
Yeah,
like they have to be equal. So you divided it to see what the equilibrium of it would be, which is 36,000.
100, but yeah. So I
100.
divided by the 0.28 because this S was the stock. And I wanted to find out how many fish were in there to start with. And so there's 3,600 to start with. I divided this to get the S for stock by itself. So,
Right, okay.
okay. Any other questions? Okay. If you do not have any questions, I will see you on Friday.
Thank you.
You're welcome. Have a nice day.